Experiment 6, the partition coefficient. Today we are going to extract through liquid-liquid extraction benzoic acid and its conjugate base from two immiscible phases, or we could also say two immiscible layers. And so the partition coefficient is particularly useful for health science majors to be aware of because it is so important in terms of drug design and drug delivery. In this particular experiment, we are going to use methylene chloride as our organic layer, which is immiscible with water. That means not soluble, and of course then distilled water. So when you mix distilled water and methylene chloride, you get two layers. The methylene chloride will sink to the bottom organic layer because it is more dense than water, and so you will see two phases. The first part of the experiment, we will use benzoic acid as its native free carboxylic acid form. On the second part of the experiment, rather than using distilled water, we are going to use a saturated solution of sodium bicarbonate dissolved in water. And what occurs there is that the bicarbonate acts as a base and will deprotonate the acidic proton of benzoic acid here. Its pKa being around 4.2. And the acid-base equilibrium is hugely in the forward direction. And so what occurs is that you then generate the salt of benzoic acid. And so left out here in the equations are the sodium cations, but they would be ionically bonded with the conjugate base, the carboxylate salt. So you would get sodium benzoate, which is the conjugate base of benzoic acid, and we would expect this to be more water soluble than the free native carboxylic acid because it is now a salt. And then once you protonate bicarbonate, which is acting as a base on the left-hand side, you then get its conjugate acid on the right-hand side of the equation called carbonic acid. And so remember that the stronger acid forces the proton on the weaker, so it makes a lot of sense that benzoic acid, which has a lower pKa value, is going to protonate bicarbonate, and the equilibrium constant is usually in the forward direction. Furthermore, carbonic acid is thermodynamically unstable. And so what occurs upon shaking, increase in temperature, and what have you, carbonic acid will decompose into water and carbon dioxide gas. So entropically, the equilibrium constant is sort of misleading because one of your products on the right-hand side is actually decomposing and leaving the reaction. In order to thoroughly understand the solubility of organic compounds, either in a lipophilic / hydrophobic or lipophilic / hydrophilic environment, you have to be able to look at a structure of an organic molecule, identify its functional groups, tell yourself something about the polarity of a functional group, and then recall the intermolecular forces that will occur between the organic molecule under consideration and then the solvent in which you are trying to dissolve it in. For a review of solubility, I highly recommend that you check out this book, Review of Organic Functional Groups, An Introduction to Medicinal Organic Chemistry by Thomas Lemke et al. And this book is available electronically through our library, and Chapter 18 is of particular interest regarding predicting water solubility. Before you read this chapter, you should also polish up your understanding of acid-base chemistry. But if you read this, it's rather short on intramolecular bonding. I highly recommend that you do that. Once again, it's free through the library. Another book to check out, also electronically available through our library, is Introduction to the Pharmaceutical Sciences. And this also has a wonderful explanation of the partition coefficient and its usefulness in drug design and also drug delivery. And so what we can really need to talk about is how one might predict the solubility of an organic compound either in a hydrophobic or hydrophilic environment. So if you look at this picture here, you have two phases. In purple is normal octanol, and in gray is water. So the organic layer is on top now, and that's because it's less dense than water. The reverse is going to be true when we use methylene chloride as our organic layer. So we've got these two solvents in two phases, two different layers. And then what happens is that you add the drug, dissolution occurs, and then solvation. What you want to know is the distribution or the amount of drug either in the organic layer and the water layer, so that you can gain some information about its ability to then cross the lipid bilayer. Why they use N-octanol in an industrial setting is because it's amphiphilic in the sense that it has a long hydrocarbon chain of 8 carbons, of course, and then one polar end, which is a primary alcohol. And so this is a good, useful solvent in the sense that it somewhat mimics a fatty acid chain that would be part of the lipid bilayer. Okay, so we need to weigh out 50 milligrams for each, for the two parts of our experiment. And so we're going to put down a piece of weighing paper, the plate of our analytical balance. We're then going to tare the balance, and we can either use a scupula or this Teflon-coated micro spatula. And so I'm actually going to bend it a little bit so I can pick some up. And so here's benzoic acid, 99.5% minimum, sold by Alpha Azar. And there's 100 grams in here, so we should be good. So 50 milligrams, well actually let me show you what this looks like first. So here's benzoic acid. You can see it's sort of a shiny white solid. And 50 milligrams is really not going to be that much. So I have both windows open so I can try and do this over the balance. And I just spilled some. But what I'm doing is I'm just going to actually scrape the walls of the glass towards the top of where it is, where the cap goes rather. And I've got 59 milligrams, 0.059. That's okay. We can use closer to 60 for one of the parts. And now I'm going to tear another piece of weighing paper. And I'm just going to, again, just scrape the sides here because just really don't need that much. And the stuff in the actual bottle. Alright, so we've got, just put one little pellet of it on there. So here's 61 milligrams. So this will be for part 1, and the larger pellet will be for part 2. Now it's reading at 62 milligrams. So we got 59 and 62 milligrams respectively. All right, so let's go ahead and draw the structure of benzoic acid. So I have a benzene ring, and then coming off of the benzene ring is a carbonyl group, and then attached to that is an OH. Right. So here this is very clearly a carboxylic acid functional group, and this is called benzoic acid. An important physical property to know for this experiment is its pKa value. And it emphasizes the fact that in the name, acid, that benzoic acid is a weak acid. And so for part 1, at the balance, we had measured out, or we are going to start with 59 milligrams. And for part 2, we are going to start with 62 milligrams. So now we're going to transfer this to a 5 milliliter reaction vial. So we used this in experiment 5 for, experiment 4 for fractional distillation. So here's our 5 milliliter reaction vial. We've got the screw cap, and then we've got a septum. And so the septum on the top face, if you can see this properly, which is shinier, that's Teflon coated. So we're going to have this non-reactive side face our, or the interior of our reaction vial. And then the softer side is faced outward. So for part 1, a lot of people like to bend the weighing paper to transfer, but I like just taking and pinching the 2 edges here on the same side, creating a little funnel, and then we've got pretty much a good quantitative transfer. If I wanted to, I could also scrape some off with my microspatula, but this sort of spilled off pretty well. So this will be for part 1. Set it aside for a second. And then for part 2, we've got another reaction vial, and this was 62 milligrams. We are going to dissolve the benzoic acid in methylene chloride, and we are going to use 600 microliters. So we get out our 1000 by 100 microliter auto pipetter, and we are going to set this, right now it's at 800, so we're going to dial it back to 600 microliters, okay? And now you can even lock it in place if you wanted to. Or actually, no, that's not the lock. That pushes out the pipette tip. This is the lock. Upward there, and now you can see I can't turn it anymore. So methylene chloride bottle. Remember, there's 2 levels of depression here. The first, just slowly draw up the 600 microliters, and then delivering. And so we'll let that larger piece of benzoic acid dissolve in the methylene chloride as we perform part 1. And then here was our 5 milliliter reaction vial with the 59 milligrams of benzoic acid. And I'm going to add 600 microliters to this one as well. Okay, and so what we can note here is that if we look into the reaction vial, we can see that the pieces of benzoic acid are not immediately soluble. And if I shake it and stir it, I can see that it's still taking some time to undergo dissolution, and then for it to be completely dissolved in the methylene chloride. So I need to give this a little stir, and I have to be patient until the pieces break apart and then finally go in. And based upon our knowledge of the functional group the carboxylic acid in its unionized form, and then also the benzene ring, we could say that this is going to be more soluble in the organic layer. So this will eventually dissolve in our methylene chloride. It's important to note that benzoic acid has 6 carbon atoms total. The benzene ring is certainly hydrophobic, also known as lipophilic. And then the carboxylic acid functional group is considered a moderate polar group. So the carboxylic acid is certainly, you've got a permanent dipole there, so its functional group, benzoic acid's functional group, will also lead to some of its water solubility. But as its native carboxylic acid in its unionized form, it is more soluble in the organic layer. But we need to wait for this all to dissolve until we add 600 microliters of deionized water. We will then see that we're going to have 2 phases. We can once again also call them 2 layers, because methylene chloride and water do not dissolve. Since methylene chloride is more dense than water, we will see that the water will float on top of the methylene chloride. All right, so while we're patiently waiting for the benzoic acid to dissolve in the methylene chloride, we can go ahead and get the tare weight of our final 2 culture tubes that we're going to label A and B. So part 1, I should have really said A, and part 2, B, but you should get that. So first thing I'm going to do, I put down a piece of weighing paper because I don't want to contaminate my culture tube from whatever might have been on the balance beforehand. I tared it, and so for tube A, it is 11.567 grams. This is the tare weight of part A culture tube. And then I'm going to do the same thing for culture tube B. It's good to tare it in between. Tare the balance, I should say. And culture tube B, the tare weight is 11.602 grams. Got the tare weights of culture tubes A and B. I'm going to put it in the test tube rack, and then also your instructor should give you the 5 3/4 inch pressure pipettes with the column of sodium sulfate in there. And that's going to dry the organic layer and also filter out anything that we might have accidentally drawn up. So part A, all the benzoic acid now you can see has been completely dissolved, right? We no longer see any traces of that white solid. And so now we're ready to go ahead and add the 600 microliters of distilled water. Let's also look at part B. Has that piece? No, because we weren't stirring it. So that larger chunk of benzoic acid in part B has not completely dissolved yet. And so that, of course, will take longer to dissolve because it's a larger piece of benzoic acid. So I've got 600, I need 600 microliters now of distilled water. And just go ahead and watch very closely that as I add the water, you see that it's forming bubbles of its layer on top of the methylene chloride. So the water layer, say the aqueous layer, is sitting on top of the methylene chloride because it is less dense than methylene chloride. The density of methylene chloride is 1.33 grams per liter, or we could also say 1.33 milligrams per milliliter. and the density of water we say is 1. And so now what I'm doing is that I'm stirring it again, and then also I'm going to be sure that my cap is very tightly sealed and that I've got a septum that has never been pierced before, so we've got a good seal here. And I'm going to just gently shake the reaction vial, and what's going on here is now the benzoic acid is going to distribute into it's going to distribute partially into the aqueous layer and then, of course, remain in the organic layer that we had originally dissolved it in. And so what we want to eventually figure out is how much benzoic acid still remains in the organic layer. And so you can see now I still have 2 phases. At the interphase, the bubbles are sort of waiting to just sort of pop, so I'm going to let that sit for a second. And then I'm going to see if I just, and then I'm going to use a 9-inch pasture pipette and my pasture pipette bulb. Get it on there well. And I'm going to dive down, and I only want the organic layer. The aqueous layer we can save, but we are not interested in. So to tube A, very carefully, I like to sort of, if you're ambidextrous enough, to hold the two next to each other, and I've got the bottom of my pasture pipette drawing up just the organic layer. And then I very carefully transfer it over, oops, to the second culture tube A. So the issue here, which is why I was trying to draw up a little bit more and made a mistake, is that if we look at the end of the pasture pipette, the methylene chloride that it saw evaporated and left some benzoic acid on it. You can see on that tip there. And so that is absolutely a source of error. If you were to perform this here, you wouldn't necessarily have the time to do this, but what I'm going to do is I'm just going to take a little bit of methylene chloride and rinse the pipette tip, just because I want to be sure that I've got a nice quantitative transfer here. So I'm just rinsing the tip of my pasture pipette, so I've got all of the benzoic acid that was originally dissolved in it transferred over to our first culture tube. But that's extra. Okay, so I'm going to now add to culture tube A anhydrous sodium sulfate. And so we did a pretty decent job transferring the methylene chloride over. If you're to look closely here, we do not see any really droplets of water stuck to the sides of the glass. So the sodium sulfate that we're going to add is just going to dry the organic layer. It's going to remove the water that we cannot see with our naked eye. And so I'm not going to use too much. I'm going to use this scupula here and just use a little tip full. Organic chemists are messy. And we see that sort of stuck to the bottom here. And that's a good indicator that we need a little bit more, because we want some free-flowing sodium sulfate, what we've referred to as the snow globe effect. Really messy today. All right, so now we've got some free-flowing sodium sulfate, so this is good. So we're going to just let that sit for a while, because it does take some time for the anhydrous sodium sulfate to take the water out of the organic layer. But that's fine, because now we can perform part 2 as that is sitting. Okay, we've completed almost, and now we're on to part B. And so these are just some crude drawings here. Part B, the reaction vial, rather than having deionized water, we're going to use a saturated solution of sodium bicarbonate. And as of right now, we still have the bottom, what's going to be the bottom organic layer, and at this point in time, that larger chunk of benzoic acid has completely dissolved. And so we're going to, of course, now use a different autopipetter, because this one's for methylene chloride, this one is for just deionized water, and so now we don't want to contaminate them, so this one we'll use for the sodium bicarbonate. And of course, we're going to check that we've got 600 microliters. Lock it in place. We did that for this one too, right? No, we didn't. We actually added more water than we should have. Whoops. That's why you always check. But, so that means this is a source of error for part A. So what we're going to do is, we'll start it over, but you don't have to watch. We'll do it really quickly. All right, so part B, now I'm using sodium bicarbonate, so I'm going to draw up 600 microliters of the saturated solution of sodium bicarbonate, and I'm then going to add it to the reaction vial. And so if we get in real close and look in, I'm going to drop it in, we'll see the same effect, that there'll be more than one layer. It doesn't immediately stay on the top because it's saturated with sodium bicarbonate, so the density isn't 1 anymore. And so it sort of didn't float immediately. And also we can see that we haven't even shook it yet, and there's some bubbles forming. And so those bubbles are is the carbonic acid being formed and already decomposing into carbon dioxide gas. So now we're going to shake it. And the proton transfer is very fast. It's one of the fastest reactions, and essentially immediate. So watch as I shake it, and then you can hear it, maybe, but I'm venting it, and CO2 is coming out. All right, and you can observe now that the aqueous layer looks different, and we've got some carbon dioxide now leaving the solution, right? And this is at the top of the layer, so it's not the interphase, it's definitely carbon dioxide. So that's one observation that, of course, we would want to examine. Let's give it one more shake for good luck. Oh yeah, no, it's actually still coming out. So I want to do this until I no longer hear the carbon dioxide. So yeah, it's still working. So shake this, and as I'm doing this, let's just briefly talk about what's going on again. So my sodium bicarbonate, here's its Lewis structure, is our base, and of course benzoic acid is our acid. And so remember that this pKa is in the regular range for carboxylic acids, 4.2, and so bicarbonate is going to take this proton So this oxygen-proton bond is forming. At the same time, this proton-oxygen bond is breaking. And I generally like to form a pi bond here and have the lone pair go up here, just to emphasize the fact that the benzoate anion is resonance stabilized. And we can draw that as well. So now I've got benzoate. Sodium, of course, is our spectator. It's just watching the event. And it's nice to just draw the resonance. The double-headed arrow is a resonance arrow, not equilibrium. So there's, of course, resonance structures of the benzene ring and also of the carboxylate group. This is one of the reasons why carboxylic acids are more acidic than alcohols. It's because the conjugate base is resonance stabilized. And then, of course, the byproduct, or the conjugate acid, I should say, of bicarbonate is carbonic acid, which we said is thermodynamically unstable, so we can put it in brackets, and we see it that it's it's unstable just by simple physical agitation. The carbonic acid is decomposing into carbon dioxide gas and water, and so it's the same effect as shaking a bottle of soda, because soda water is carbon dioxide gas bubbled into it, and so you're forcing it to become a saturated solution of carbonic acid, essentially, and then you know that if you shake a bottle of soda, carbon dioxide leaves. So we can draw this now arrow, technically in equilibrium, but we definitely know that it's leaving as CO2 plus H2O, right? And what I just mentioned about making soda water, it's where you have a pressure of CO2 added into or bubbled into water to then get soda water, carbonic acid. And so perhaps some of you have seen those soda streams. That's exactly what's going on in there. And so let's just see this again, make sure it's sealed. Is it still giving off CO2? It seems like it's taking some time, but I no longer hear the carbon dioxide gas. So I think that we're good to go. And of course, we're now expecting that there's going to be more sodium benzoate dissolved in the aqueous layer, and that ultimately our culture tube B will have less benzoic acid in it because benzoate anion is not very soluble in methylene chloride. It's much more soluble in an aqueous environment. So now I'm going to use another pasture pipette because I don't want to contaminate. Oh. All right, so we made a mistake twice. We used 800 microliters of water for part A, which should have been 600, and then you just saw me spill part B completely, so that was fun. So now we're starting over for both of them, but everything else I said is good. Hopefully it makes sense. So part A now, in here we've got 67 milligrams of benzoic acid. In part B, we're now dealing with 65. So I'll rewrite those numbers. So what we're gonna do, we added the methylene chloride for part A. Now, let me double check again. Yes, 600 microliters of deionized water. And then for part B, let's try and not knock it over, the sodium bicarbonate. Down milligrams from part A now. It's going into its reaction vial. And then 65 milligrams for part D is now going into its reaction vial, which I will not spill this time. All right, so we've partitioned part A, aqueous layer on top, methylene chloride layer on the bottom. Part B, we've got the saturated bicarbonate layer on top, and then of course the organic methylene chloride layer. So once again, we're expecting the native benzoic acid to be more soluble in the methylene chloride layer here, and there's the acid-base reaction to give the sodium benzoate, so we expect that salt to be more soluble in the aqueous layer, and so when we try and recover the methylene chloride layer, the organic layer from these two, we'll expect that there'll be more benzoic acid from part A and less benzoic acid from part B. So now we're going to very carefully transfer the organic layer from part A So if you're ambidextrous enough, you can do this. So I'm just diving down, trying to avoid as much water as possibly can. And I've now delivered the organic layer to the first culture tube. And you'll remember that I said something about the benzoic acid being on the tip of the Pasteur pipette. You can also see it on the interior here as well. So I'm just going to use a little bit of methylene chloride to rinse that. So I'm going to rinse the inside of the Pasteur pipette as so to get everything transferred over, and then also rinse the tip as well. So now we've got definitely a quantitative transfer there. All right, so this is part A's Pasteur pipette. We want to discard it, and now part B, we are also going to separate its organic layer and put it into culture tube B. And now with this one, we don't see that issue, of course, because we deprotonated the benzoic acid, so it shouldn't be in the methylene chloride layer, so we don't have a residue of it. However, still to be consistent with the experiment, we'll also, might as well, just rinse the Pasteur pipette with small aliquots of methylene chloride. To affect a quantitative transfer. Okay, so now we need to dry both of these organic layers with anhydrous sodium sulfate. It could be because, look, if you look closely at culture tube A, right, this residue here, that's benzoic acid, right, from just adding in the methylene chloride, it evaporated and then left its residue. Whereas here in part B, once again, you don't see that. All you see is that there's little droplets of water stuck to this glass. So this is more wet than that one. So I did a better job transferring part A than I did part B. But regardless, we're going to dry both layers with the anhydrous sodium sulfate. And we're going to give it around 7 minutes to do that, because it does take some time for the sodium sulfate to grab as much water as it can, which is 9 molecules of water per sodium sulfate. So we've got some free-flowing stuff there. That's good. Part B, we said, should require a little bit more. See, we see the sodium sulfate stuck to those bubbles of water there immediately. And we've got, see, it's chunky and heavier. So we're gonna add a little bit more so that it still looks like granular sodium sulfate that we added, and we get that, quote, snow globe effect. So now we should be good. All right, so we're going to let that be, and then once we're done allowing it to dry, we'll then transfer each organic layer to the tiered culture tubes A and B. We are also, once again, going to rinse the test tubes for a quantitative transfer, and it'll also then rinse our column of anhydrous sodium sulfate, right? Because this last part is the going to dry anything that we missed and also act as a filter if our pasture pipette accidentally draws up some of the sodium sulfate. To dry. And now I'm going to add part A to its tiered culture tube, and so it's going to go down this column of sodium sulfate. So last line of defense in terms of drying our organic layer. It's drawing up some of the wet sodium sulfate, so it's good that it's also filtering it. And now I want to use clean methylene chloride to rinse my culture tube. So once again, we're trying to get a quantitative transfer. And it's also rinsing the column of any benzoic acid. And might as well do this 3 times, because that's a magic number. You can even draw it up and then rinse the sides of the culture tube with the methylene chloride to be sure that you've gotten all of it, all of the benzoic acid. And then now for the third wash, because we're being so thorough. So now we've got part A's discarded, and now this is all going into our tiered culture tube, the methylene chloride with the benzoic acid. And then what we're going to do is evaporate off this methylene chloride so that we can determine the amount of benzoic acid that was in it. So in order to help this go, rather than just wait for gravity, I'm going to push it with the pasture pipette bowl. So now I got positive pressure. Now it's all out of there. Right. So this is part A in this tiered culture tube, and now we're going to just leave it in a hot sand bath. Aim it away from us just in case the methylene chloride starts to boil in our face, but you can already see that it's boiling. Its boiling point is 39.6 degrees, and so it should evaporate away pretty readily, and then we'll see that there'll be the solid residue of benzoic acid left over. Once again, we're expecting to see less in part B. So this is my clean pipette for methylene chloride. And now here's a new pasture pipette for part B, once again to avoid contamination. And it's going to be the same process. This time I'll do it with them in the test tube rack, because you can do it either way, of course. The first way was faster for me, but more difficult in general. So rinse number 1. Once again, get the walls of the glass to try and get any sort of residue of benzoic acid off of it, but once again, we're expecting there to be very little benzoic acid. Rinse number 2. And then finally, the last aliquot of methylene chloride, rinse number 3. And once again, we're going to see that it's coming down, but I'm not going to wait for gravity, so I'm just going to gently place the pipette bulb at the top here. I'm going to let it down though, and force air down into it. Okay, so part B is complete, and now we're going to evaporate off that methylene chloride as well. Let's see, has part A left? Yes, all of the methylene chloride is gone. There's a little bit of sand on there, but now this is the residue. This is benzoic acid, right? This was what was dissolved in the organic layer the entire time. And so we're going to let this cool before we acquire its mass, because when it's hot, it actually pushes down on things. And then we're waiting for this methylene chloride now to evaporate. We'll get the mass of the 2 culture tubes now, subtract the tare weight, and then we'll that's how we'll calculate how much benzoic acid is in the culture tube, and therefore how much benzoic acid was in the organic layer. So now we've allowed the culture tubes A and B cool down, and even just upon examination, we see that there's much more solid that was recovered from part A relative to part B. As we're doing this, obviously the methylene chloride boiled off, and we've got a nice white solid here. Melting point 121 to 124 if it's benzoic acid. So now it's nice that we have a solid because we can still tip it upside down, but just to be safe, we're going to have it on its side now. Did I tear it? Double check. So now we've got, let it settle, 11.623. So 11.623 minus the tare weight of the culture tube, which we measured to be 11.567. So we've got 0.056 grams, which is 56 milligrams recovered. We had started with 76 milligrams, so that's a pretty decent recovery. Now let's get the mass of the amount of solid in culture tube B, where we started with 65 milligrams of benzoic acid. Let the balance settle. So 11.610 minus 11.602, the tare weight, equals 0.008 grams, which is 8 milligrams. So clearly, very little recovered from test tube B, part B. Okay, so in order to calculate the partition coefficient, we look at the calculation in the lab manual. And so a sample is that we need to know the original mass of the benzoic acid that we had started with. So for example, in part A, we had started with 67 milligrams. And from that, you subtract the amount of benzoic acid recovered in this culture tube. So the amount that we recovered was 56 milligrams. And so what we can therefore say, we can assume that 9 milligrams of the benzoic acid remained in the aqueous layer. Okay? And so now to calculate the partition coefficient, we take the amount recovered divided by the amount assumed in the aqueous layer. So we recovered 56 milligrams. We assumed 9 milligrams of benzoic acid was in the aqueous layer. So 56 over 9 is 6.22. So our partition coefficient for benzoic acid from part A is 6.22. By the way, I'm abbreviating benzoic acid Phe CO2H. Phe is for phenyl, which is the C6H5, the benzene ring bonded to the carboxyl group. And now, so for part B, we recovered 8 milligrams only from the organic layer, and we had started with 65, and so 8 from 65 is 57 milligrams that we can assume is in the aqueous layer. So to calculate the partition coefficient for part B, it's 8 milligrams recovered over 57 milligrams that we're assuming is in the aqueous layer, and so our partition coefficient is 0.14.